It is the closest planet to Earth in size and distance. It once may have had oceans and a similar climate. Now it is hostile and unforgiving. Scientists want to know why and how it changed. This could help with the hunt for other habitable worlds. For now, Venus could be considered Earth's evil twin. One of the brightest objects in the sky, Venus has been a world of mystery and conjecture. Probes were sent to briefly study the cloud tops as they passed by. The NASA Mariner mission, quickly followed by the Soviet Union's series of Venera flights. They left more questions than answers in their wakes. Eventually, Venera 4 landed a probe through the dense atmosphere onto a searing hot surface, followed up with more sophisticated probes that lived for a very short time. Other probes floated briefly in the dense, poisonous atmosphere. Mars became a much more attractive target, and Venus has been left little explored. In the late 80s, the Magellan probe was launched from the Space Shuttle. It mapped the planet's surface with radar, giving us a detailed look at the rugged surface of the planet. Stripping away the dense, thick atmosphere revealed intricate mountains, volcanoes, and lava fields, an uninviting and hazardous environment hot enough to melt lead. Following orbiters from both Europe and Japan also studied the surface features with radar. The Venus Express dipped into the upper atmosphere to aerobrake and descended into lower orbits. In recent years, several probes have used Venus for gravity assists to propel them to other destinations. Bepi Colombo, on its way to study Mercury, passed by, taking images and other readings. The maneuver, the second at Venus and the third of 9 flybys overall, helped steer the spacecraft on course for Mercury. Another European spacecraft, the Solar Orbiter, also utilized Venus for a slingshot as it closed in on its solar orbit. The Parker Solar Probe made a close flyby, taking measurements of the electric field of the planet and the radio emissions from the hot surface.
It's thrilling to be able to see something that's never been seen before. This emission that we're seeing is thermal emission. Even on the night side, the surface of Venus is so hot that it's glowing faintly at very red wavelengths.
These whisper images, I think, are really exciting because they provide a new window into the lower atmosphere and surface region of Venus where these extreme conditions exist.
A faint glow of heat from the night side shows distinctive features like continental regions, plains, and plateaus. A luminescent halo of oxygen in the atmosphere can also be seen surrounding the planet. These observations revealed much about the chemical composition of the surface.
Another really interesting thing we could look for is potentially mineralogical differences. Different rocks and different minerals emit different levels of heat.
Some surprising results suggested that water may have been on Venus in the past, but climatic changes and planetary processes removed the water from the planet and its atmosphere.
We have chemical fingerprints in Venus's atmosphere and on its surface, suggesting that Venus might have been habitable in the past.
The Wide Field Imager, or WISPR, is the sole imager aboard the Parker Solar Probe.
This is something that's truly new, and I believe will yield exciting science in the long term.
Once upon a time, Venus might just have been like an early Earth, with oceans, lakes, and rivers of liquid water, a much milder, oxygen-rich atmosphere. What changed the environment? Perhaps volcanic eruptions and toxic gases creating an atmosphere of carbon dioxide and sulfuric acid clouds, trapping heat in a greenhouse effect. Venus has the hottest surface of any planet in our solar system, hotter than Mercury. The atmospheric pressure is nearly 75 times greater than that of Earth. NASA and ESA are returning to the planet to find some answers. Europe is sending the spacecraft Envision, in partnership with NASA, which is providing the synthetic aperture radar system called VENSAR. The S-band radar will also act as a microwave radiometer and altimeter to map the surface. Envision will also carry 3 optical spectrometers designed to observe the surface and atmosphere of Venus, and a subsurface radar sounder that will probe the top kilometer of subsurface. NASA will also be sending Da Vinci and Veritas to Venus, due to be launched around 2029. Veritas stands for Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy mission. It will also map Venus's surface to determine the planet's geologic history. Germany and France are contributing to the infrared mapper and radar systems to determine whether active volcanoes are releasing water vapor into the atmosphere. Da Vinci, the atmospheric probe, will descend into the Venusian atmosphere to study the gases and chemistry with advanced sensors. It is designed to survive the descent to ground level whilst imaging its journey. The 1-meter wide probe will target a region called Alpha Regio, twice the size of Texas, and will add to scientists' understanding of rocky, atmosphere-bearing exoplanets that will be explored by new observatories such as the James Webb Space Telescope.
So Venus is cool. Venus is awesome. Venus is, in many ways, one of the most Earth-like planets that we know of. One of the key ways that it's different is that it's very, very dry. With temperatures on the surface of 460 degrees centigrade, whatever that is in Fahrenheit, you would never expect there to be liquid oceans on the surface. That kind of temperature only boils off that water into steam, but the atmosphere of Venus is still incredibly dry. So where did the steam go? So to talk about how we remove something from a planet, we're going to have to talk about two forces of nature. Firstly, the force of gravity. Gravity is the thing which is holding you down to the planet, but if you think about it, it's also what is holding the atmosphere down onto the planet as well. If I want to remove some of the oxygen from the planet, we have to overcome that gravity. So to do that, I want to talk about the electric force. It's the thing which your device is using right now to pump electricity around its wires, right? It's pushing the electrons around the circuits. And what we think can happen is that the electric force can help push on the ions and in the upper parts of the atmosphere, push them off and up into space. So just as every planet has a gravity field, we think that every planet has a weak electric field. So we went looking for Venus's electric field, and boy oh boy did we find it. It turns out that Venus's electric field is at least 5 to 10 times stronger than at Earth. It's a monster of a force. It can rip heavy things like oxygen straight out of the upper atmosphere and send them kicking and screaming off into space. So this really changes the way we have to think about planets, because it turns out that planets can lose heavy things like oxygen to space entirely through electrical forces in their ionospheres. This is something that's really important if we want to go looking for exoplanets, for habitable planets around other stars. It is no good having conditions perfect for an ocean and an atmosphere that you might want to breathe if some invisible force is going to come along and rip it all off into space. Only understanding how atmospheres evolve can we try and understand how we got here.
Many orbiting telescopes and instruments are now in use to search for, identify and catalogue exoplanets, planets orbiting other stars. TESS, Kepler, Hubble, James Webb and the Nancy Roman telescopes are looking at planetary formations around various stars. Knowing how Venus evolved would give additional assistance to the planet searchers. This image is of a new star and its gas disk. The black rings show where planets are forming by gathering the dust and debris. This image reveals a moon forming around a gas giant as it evolves. This massive exoplanet orbits a white dwarf, the remnant of a dead star, and is slowly evaporating.
Another big unknown is to characterize planets that are orbiting other stars. So now astronomers have got very good at finding these planets, but what we want to do is look at what they're made of. So what's in their atmospheres, or if they were rocky, what kinds of minerals are we seeing? And to be able to do that, I think will be stupendous.
So this, we can see the composition of the atmosphere in exoplanet, so what it's made of. And the specific planet we're looking at is hot. And so what we see in that is that there's water there. It wouldn't be in liquid form because the planet's hot, so it would be more like steam that's around it. But we can tell what's in that atmosphere.
So the James Webb Space Telescope is brilliant in a number of ways. One, it extends our wavelength all the way into the infrared, into the mid-infrared, so we can look for these heat signatures from these planets as well. But that also means we can cover the fingerprints of different materials in the atmosphere. So the Hubble Space Telescope looks for fingerprints of sodium and potassium and water in the atmospheres of these worlds. But the James Webb Space Telescope is going to be able to look for signatures of methane and carbon dioxide and carbon monoxide, as well as all of these wonderful water features that we'll be seeing in these giant planet atmospheres. But not only can it tell us in these different wavelength ranges, it's actually better resolution, so we can get more data points for each of these different molecules. And it's a much bigger telescope. We're collecting far more light. We can get a much better precision. So that means that the degree to which we believe our measurements is going to improve a lot with this telescope. And that's going to mean that we'll be able to tell you with confidence what we're measuring. Looking for life on other planets is the ultimate future goal of all of these missions, trying to understand how we got here, how the Earth is the way it is. The James Webb Space Telescope is taking us one step further towards that goal. We're going to be pushing to these smaller worlds where we can see what different planets that are unlike ones in our solar system are like, how atmospheres change with the size of your planet. And it's also going to give us information on these giant planets that we don't have in our solar system, so close to their star that they're hotter than a rocket. They're different worlds that we can explore with this, and every technique that we use with the James Webb Space Telescope is going to be the technique we need to be looking for life signatures on these other worlds. So getting good at using this technique is so important so that in the future we can be looking for these signatures.
So what we see here is what's called a hot Jupiter. So it's a planet that moves in front of its star, and it has about the size of Jupiter but the mass of Saturn. And what we see here is light filters through its atmosphere, and that allows us to look for the fingerprints of certain molecules. And in this case, the planet is full of water vapor, full of water. And that's what you see as wiggles in the spectrum. When we go and look at other exoplanets with Webb, we may look for other molecules, some that are familiar in our own atmosphere here as well, like carbon monoxide, carbon dioxide, or maybe even methane and ozone.
The total so far exceeds 5,000 exoplanets, with a further 8,000 to be confirmed. Of particular interest are the smaller, rocky, Earth-like planets.
We know our targets, they're bright stars which are known to host the type of planets we want to observe, and we will know when these planets transit, that is when the planets move across the disk of the star, and we can measure the changes in the output of the star, the measured output of the star, in order to measure the size of the planet. We'll be focusing on smaller planets, so Earth-sized to Neptune-sized planets, which have been found by other missions, such as Kepler, to be very abundant around other sun-like stars, something which is not so much the case in our own solar system. So it's a big question. What are these smaller planets? What are they made of?
The range of planet types is amazing. Rocky worlds that sustain oceans and lakes, likely candidates for life. Others more extreme, like WASP 76P, tidally locked to its star, only ever showing one face to its sun. This extreme exoplanet has a day side where metals evaporate and a night side where it rains iron. Rogue planets that have no sun to orbit, ejected from their solar system and left to roam through space. Planets that have the heavy element barium in their atmosphere. Water worlds, planets still forming, others around dying stars. We must remember that amidst all these searches for a new Earth, we must take care of the one we have, because it is a very long way to travel to reach these other habitable worlds.